if you can hear, could you please check again? Thank you. Can I see a green check from you guys? Okay, my friend Joe. All right. Thank you guys for coming. This will be class number 22. So we have 2 more classes to go, my friends. So that's the good news. I'm going to be doing, Byron, my friend, as we're going to go over the wiring table tonight. So go over 310-16, 310-17, the sizing, also sizing based on temperature rating, sizing based on bundling, and a couple of. So we're going to spend the whole night tonight talking about wiring. I need your undivided attention, my friends Eric and Matthew. If you guys give me your thank you. So what we're going to be doing, but before we start talking about wiring, we'll go ahead and review the quiz from last week as we have done. But if I do that, here's what I need you guys to do for me. WebEx will be down. If I show you guys, WebEx will be down on the 19th. So 19th, we can't hold a class on the 19th. This is what I'm suggesting, my friend, just to stay on track and finish what we're doing. So 19th would be, this is a Tuesday, not next week, the week after. This is March, April. Well, March, we're done with March. This would be April. Okay, here you go. So this is for April. 19th, WEX is not going to be able to, is going to be down for maintenance. What I'm suggesting is to do Monday, my friends, the day before, Monday 18th, so we can stay on track and finish on time, guys. I don't know, I'm sure you're as excited as Chad of finishing and just move on. It's been a long run. So what do you guys think of Monday, the 18th of April? Can I check so everybody's going to be able to make it? Every check, okay. So instead of doing, the 19th, we can't do the 19th because, as I said, WebEx will be down. So instead of Tuesday the 19th, we will do Monday the 18th, and that will be basically our last meeting, our last class. Then I do have guys one more class for final review, but this is optional. If you guys want to come, so my calendar before we will start talking about this one. So one more time. So if you guys yourself out, and Amy from MEA will also contact you. They'll be holding the last class Monday the 18th. One more, can I get a green check that everybody acknowledge that, guys? A green check that everybody can acknowledge that we're going to be doing the 18th instead of the 19th. Okay. And then the first thing I want to discuss. The second thing, guys, also April. That will be the April 26th. April 26th, I usually have a final review day. It's optional because I'll be here as long as it takes. So April 26th, that will be a review for the final. If you guys want to join me, that will be great. If you feel you're confident, you don't want to join, that's also great. It's optional. It will be optional. Okay. Optional. That will be the final review. Okay. May I get a green check that everybody acknowledge that the 26th will be final review optional? Okay, everybody got that message? Great. So I just want to make sure that guys change it to April 18th. That's for not next week, the week after. And that will be the 18th will be the last class. And we can go to the 26th to do our final review for those of you who would like to do so. Okay. Any question regarding this topic? Anybody has any question before we start? I just want to make sure that everybody's on the same page. Any questions regarding the last class and the final review? Any questions? Friend, any questions? My friend Derek? Okay, no questions. Good. Thank you, guys. Before we go ahead and start, guys, I'm going to go review as we have done in the past. We review the quiz. So I'm going to go and review quiz 21. let me ask you guys, anyone likes to talk about one of the you any questions in particular in the quiz? Any questions in next for no or to with me say chat? I would like to emphasize more. I have your results and I identified a few ones I want to go over in detail, but for them I'm going to flash the answers and move on. So questions in particular, chat it with me or raise your hand. I can pass the mic to you as we go through. On my friend, if this dirsenver movement galvanometer is connected to an AC power without a rectifier. We said rectifier is to get you the positive and the negative, a DC. It will be, and our answer for this one, it will be 0, because remember that guys, that particular movement was it depends on the north and south poles. So if you have an alternating current like this, the north and the south will always be alternating, so you would not get any movement. You wouldn't get any movement. You need a steady voltage, like a DC. Here's a plus here, and here's a minus here, to get that coil, and to get that coil to get you a north and a south pole. So the answer should be, it will, if you don't rectify it for this particular feature, it will be the 0. It will be the 0. Also, stop me guys at any time as I go through. Number 2, it has to be connected directly across the source of power. This is my voltmeter across the source of power or in parallel. You get how the voltmeter is connected. It should be connected in parallel. By the way, number 1 was, a lot of you guys got this one wrong. That's why I emphasize number 1 is because if you have an alternating current, you get a north and south pole of that coil that you're energizing. You wouldn't get north and south pole. It keeps alternating. It keeps going south, north, and north, south, and so forth. So you wouldn't get a movement. That's why it will be a 0. Welcome to the second topic, guys. It's number 2 is voltmeter is always connected in parallel with the source. So if I have a voltmeter right here, you connect it in parallel with the source or in parallel with the load. A resistor right here, so you connect across the resistor, across the load in parallel. Any question, guys? Any question about that? Any next for chat? Make sure that I'm not leaving mine here. Okay, I'm watching your questions here. Okay, should be selected to check the voltmeter on a 380 volt system. 80 volt system, my friend. Why D? Need a D. Our answer for this one, number 3, is D. 600 volts. When you have a voltmeter, guys, the voltmeter must have the same voltage or higher. The same voltage or higher. So I can't use this. I can't use any of these. I use this. I can use this, but the range that I selected is the wrong range. That's why this is wrong. So it has to be, the range has to be 600 voltmeter. Straightforward. You can't have a voltage that's higher, a voltmeter that's lower than the voltage that you need to measure. That makes sense, huh? Number 4, 2 methods used to connect shunts to ammeter movement. Methods are make and break with a switch and the earthen shunt. So these are 2 methods that you can connect shunt meter movement, and that's directly from the book. Move into the different what AC meter is used to increase the range. What do you do to increase your range? We can add a current transformers, and if you remember, we can have a coil and we can tap from different parts of the coil, so to increase an AC meter range. AC meter range to meter range to get us lower or higher amps. Any question, guys? Any question? Any question, my friends? The standard secondary current rating of a CT is a current transformer. This is really interesting, guys. The CT is always a current transformer in AC, and it's designed to operate with a 5 amp AC ammeter connected directly to the secondary winding. Okay, these transformers typically have a current ratio that is number 6 as 200 to 5. This is typically, I said, typically, I emphasize the word typically, guys. These in the industry, for 200 to 5, you can have 400. You don't 400 to 5, you can have 600 to 5. You can go as high as 4,000 amps to amps. So why this is wrong? Because first, the secondary has to be 5. Why this is wrong? Because it's very small, 2 to 5. I mean, you really want to measure 2 amps. What is wrong is also too low. Look at the 20 amps are low. Amps are low. So 100 is high, is good, because the 200 amps is the time. If you have higher, usually if you have higher than 200 amps, this is when you start using CTs. Higher than 200 amps, that's when we start using CTs, because you can't have a higher than 200 amps going through the windings of the coil. You will burn it. You burn that coil. So if you put like 400 amps right through that coil of the ammeter, you're going to kiss the ammeter goodbye. Okay. Any questions, friends? Any questions about that? Any questions? Number, my friends, looking at your questions here. 7, if digital ohmmeter displays this amount, M stands for a million, then you have basically going to have a 300, or point, what is it? 0.3 times 1, 2, 3, 1, 2, 3, a million, and that will get you this answer here. That will get you this answer. Was our answer this 7 is 8. So basically, you're going to take the 0.3 and multiply that 0.3 by 1, 0, 0, 0, comma, 0, 0, and another 0. So get 0.3 times 1, 2, 3, 1, 2, 3, get 300,000. 300,000. Question, guys? I like this one wrong. I don't know why a lot of you guys get that particular one wrong. M stands for a million. You multiply 0.3 by a million. That's how you multiply 0.3 by a million. Moving on to the second one, the time base of an oscilloscope is this amount in milliseconds per division, and the voltage range is this amount per division. From the point the waveform starts to rise in the positive direction and passes through all states, it starts to rise positive again over the 8th division, the frequency of the wave, and our answer for that one is, our answer for number 8 was C. Our answer for number 8 was C. So we have 250 hertz. We have 250 hertz. 250 hertz for this particular one. Any comments? Let me see what you guys got. That one number 8. Almost everybody gets that one too. So in 250 hertz. Into number 9, the electrical circuit which operates on the principle that the sum of the voltage drops in the series must equal the up voltage. And if you guys remember, if you go to that will be the Wheatstone bridge. The Wheatstone bridge. Right? 9 is D. Any comments, guys? Any questions about what we covered? Any comments, questions, comments? Okay. And I move fast. Please stop me at any time about any one of these. I just move fast because of the timing. The turning force of this meter movement is proportional to within is the movement of the current through the moving coil, the amount of current. So meaning as the current goes up, the M, which is the movement, also goes up. And that's to get the proportional measure the current or the voltage, guys. For deflection, you get which movement, more current you get, the more deflection. The amount of the principle, this is meter operates proportionally on the current. 11 is B, as we said, on a DC principle, in the DC principle. So if you apply the same principle of the movement to an AC circuit, as you can remember, you have to rectify the AC circuit and dump the rectified signal across this meter so you can get some measurement. But those are doing that for AC. Better way than this meter. 12 meters are connected into the circuit, and 12 should be C, right, in series. Always in series. The ammeters in series. Unless, my friend Eric, of course, we don't connect them in series. We clamp on. We have a clamp on ammeter. That's measure them. But it works in the principle that the meter is going to be in series in the circuit. So here's my meter, here's my load, and my voltage right in here. So that's basically the way it's in series, as you can see. Moving on to 12. 13 as the oscilloscope is always a measurement of the voltage. You have the voltage, and you see if your voltage looks like something like that. The voltage, or you can that's neat about the oscilloscope, or it should look like something like that. So that's basically measurement of voltage. Number 14. For clamp on ammeter is clamped around 2. This is really interesting because some of you guys number 14 got it wrong. Number 14, here you go. Number 14. I got it wrong. Around 2. I want to emphasize the word parallel conductor. Then we will read. Here's an example, guys. We have phase A. So these are phase A. I tie to both ends and tie a circuit breaker, right? This is A. Phase B, the same tie together here at the end and tie to another circuit breaker. And phase C, as you can imagine, is going to be tied to the second circuit breaker. And these two circuit breakers are this in reality is one circuit breaker. Okay, so here's so if you bring the clamp on ammeter and tie the clamp on ammeter across the two conductors. This is phase A, this is phase B, and this is phase C. If there is 100 amp here, and also, the other way around, so it should go right there. And there's also 100 amp in this one, so the total, guys, will be seen here as a 200 amp, right? Because they're the same phase in the same direction, right? Now, that's probably a lot of you guys, so it measures algebraic sum of the currents in the two conductors. So if there's 100, it will measure 200. Now, if you go and grab an ammeter and put the ammeter across all these, right, that's when it measures 0. The answer is 0. The currents from all the three phases, they kill each other. The magnetic field from the three phases kill each other, we'll see as 0. Any comments, guys? A lot of you guys got that one wrong. Any comments? Any questions about that? Anything? The key point is there are two parallel conductors. And some of you guys thought also my hot here, here's my neutral here, and here's my light, right? This is the application is my light. And if I go ahead here and clamp on ammeter across the two of them, this is probably what some of you were thinking. Is my ammeter, this will read 0. It's 10 amp here. This is 10 amp. Also, this will be coming out as 10 amps. So as you can see, the 10 amps going this way, 10 amps going the other way. So when they add up algebraically, they add up to a big fat 0. So that's what you guys were thinking of. Okay, comments, any questions, any comments, my friends, about this one? Because a lot of you got that one wrong. Hopefully they'll. So you can measure it across one phase, not two phases, not three phases, not a phase and a neutral, across one phase at a time, 15 is in the operation of DC AC clamp on ammeter. If you have a DC AC clamp on ammeter, number 15 is B, the all effects, and you can get that one directly from the book. Number 16, friends, number 16, a circuit. 16 is our answer for this one. Must not be energized when testing it with either a digital or analog ohm meter. And the key point here is not, it's energized. The key point first is energized and second ohm meter. We're measuring the resistance. You know, Joe, my friend, you can't measure the resistance when the circuit is hot. Resistance is a phenomena, and it's always measured when the circuit is de-energized. Okay? The impedance voltage tester, number 17, is D of the above, does not contain this movement, as you know, because it's measuring AC. It does not contain digital display. Yeah, it has a plunger with indicator voltage, so the above. As I'm familiar with this one, I'm sure a few of you, it's a voltage indicator, voltage sensor. It's really a tester, not a meter. I can't use the word tester, not a meter. So the above. My friends, if an attenuator probe is set at 10, so I'm setting it at a range of 10, and the range of the oscilloscope to which it's connected is 5 volts per division, then the voltage that's going to be reading, is 50, which in reality you're taking the 5 and you're multiplying by the range, and that we got your 50. Okay, and to 19, on an oscilloscope, the purpose of that calibration adjustment, number 19, is B, adjust the voltage per division that will be displayed. The voltage per division that will be displayed. Because you guys, you know, if you use that oscilloscope, you can zoom in, make the bigger, smaller, so you can have a better understanding of the, you know, signal, better understanding of the signal. And guys, any questions? Any questions, my friends? Any other question here? How many of you guys have seen this question in the quiz? I don't think that was on your quiz. Was this question on your quiz? Can you look at it? Have you seen this on your quiz? I'm not on the quiz, to my knowledge. Yes, on the data that I called. Yes, you have seen it? Okay, it's not on the quiz, but it says if a clamp ammeter draws a loop around the wire, it draws amps. If it draws amp, what will the meter read when there are 10 loops? Okay, here talking about, guys, here's my meter. This was on your quiz, and here's my loop for the meter. And suppose I have I have a wire. I'm going to loop that wire 10 loops. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You can imagine 10 loops. 10 loops. And if it's usually, it's given, if put one loop, if you put one loop, I'm going to draw one loop here. If you just, here's my meter. If you just put, let me change the color one more time. Here's my conductor. If you put one, oops, what is a different color? If you a conductor like this, and one, it usually gets you 10 amps, 5 amps here. You get amps. If you 10 loops, what happens is you get, suppose the current here, I'm going to make it complicated. Suppose X is current. If X current can give you 5 amps, okay? If you loop it becomes X divided by 10 E amps, right? And X current that will be read is 5 times 10, and now 50 if I did my math right. So 50 amps. This is not what we, so range is going to take, it's going to read a 50 amp. But in reality, guys, we don't use it this way. We use it this one. Say suppose you have a 600 1 to 5 CT, and to make it, you want to make it more sensitive. 600 to 5 is not as sensitive. Suppose I want to make it more sensitive. You know what they do? You go bit. So if I loop it one loop, let me just go one here. Here's my meter, and here's my conductor. So this CT is actually measuring 600 to 5. If I bring one wire and loop it one time, I have 2 loops in here, coming in and out. I have 2 loops, so it becomes 600 to divide 2 because I have 2 loops. 5. That's the range, which is basically 300 to 5. Who Who cares now? Your CT or your meter is more sensitive to amps. So it can be 100 to 5 more sensitive to the amps. Joanne, my friend, it's impossible to do this in practical. Yes, I can't agree more with you. Suppose this is easy to do it up to, well, let's say number 8 conductor. Number conductor, maybe you can go to number 6 conductor. If you're dealing with it, you can loop it. But if you are to have a CT, normal CTs, and you have a 400, this is basically meaningless. Honestly, inside the CT, here's my 500 kcm. There's no way you can do that. So kcm, here's my 500 kcm. Then you get is what you get out of your CT. You hear your 5 amps. And suppose the CT was set for let's say 500 kcm is good. So 300 to 5. So suppose the current was going. I don't know much is that. Suppose the actual current that was going here, suppose was 150, right? The current that's going through here. Then out here, as you can, it's going to be half of the 5, which is 2.5. So basically more. So looping is meaningless when it comes to real CTs. Thank you, my friend, and I can't agree more. Any questions? Any questions? Questions before we move into the topic of the night? It makes more sense, as I said, if you're looping, if you're doing it in a lab or a small wire. But yeah, an ammeter makes sense. But if you have which is usually on bigger conductors, doesn't make sense. Moving on, my friends, into our topic for the night. Let's go erase all this. Our topic for the night, my friends, is going to be wire table. For the wire table, I have a few things always guys do when I teach wire tables. Some of it would be Eric, my friend, will be a review for you, but I guarantee you, I teach the exam prep, and if you so it'll be so hard for you to prepare an exam. Okay, we're going to talk a little bit about how to use conductor by using the wire tables. In particular, guys, we're going to be using 310.16, 310.17. Characteristics of code recognized insulation. What is the THHN? What is THW? What's RH? All these stuff. The type of conductor suitable for different conditions used. That's also the insulation. How the correction factors and the rating factors which determine amps. Are very important things. So I hope, my friends, guys, you can get out of this class really tonight in how to properly use 310.16 with the rating, how to identify and understand the insulation, THHN, THW, and so forth. And I'm going to jump into 310.16 and a couple of settings, so a couple of other tables. Another thing, guys, is sizing based on voltage drop. How do you size a conductor based on voltage drop? Because we size based on current, we size based on temperature, we size based on how many in one conduit. We also have to size based on voltage drop, distance, how far you can put a cable and you still get the voltage out of that. Using parallel conductors, we have to list requirements, and I'm sure a lot of you probably know that. How to use insulation resistant resistor to measure a circuit and make sure that you don't have a ground fault or a short circuit between the three phases. Terms, again, the voltage drop formulas that we're going to be using this is for your general exam, no question asked. Theory behind the rules for parallel conductors. We'll talk a little bit about why we have the rules for parallel conductors. These are things that we hopefully, guys, we can achieve from there. Any question? Any question about the rules? Go ahead and start. My friends. Okay, before I forget, guys, somebody emailed me and reminding me here. Homework. If you guys have not submitted your homework, please do so. If you want to check that you submitted all your homework and you are in doubt, please email me. I should be able, I'm good at getting back to people on time. So if you need the homework sheets and you can't get them from on the site, please email me and I should be able to email you. And I emailed it to a lot of you guys. So do that. Okay, so question is, can you guys give me a green check for can you give a check for the homework? Everybody acknowledge what to do of homework. Green check. So if you guys want the homework again, if you've not done your homework, please email me. I should be able to email you all the homework and so forth. Okay. Next, my friend Byron, these are the AC cable, I believe. The trace name for AC cable. There's MC cable and AC cable. AC cable, I believe, the BX. If I remember that right, if I don't get the mix. That's your cable. Going on, guys, into conductors. The thing that's important, guys, when we size conductors, I'm going to share the NEC code book with you, and I highlight certain things I believe I've done in the past, but I'm going to end it one more time. The most important thing about a conductor current is heat. Every time you have a current going through a conductor, it generates heat. Who cares? Heat is enemy number one of electricity. Why? Because heat can deteriorate the insulation. Who cares? Then sitting there said, who cares? Let the insulation deteriorate. Well, we care about smoke coming out of the conduit and short circuit, then melting all these insulation. And next, when melt the insulation, you're going to have face-to-face short circuit and tripping a feeder or a branch circuit and losing the power. If you don't care about this one, then no problem about voltage drop and the whole Ampacity tables. And then, my friend, when we have conductor uninsulated, bare conductors in there, they can carry almost 50% to 100% more than they can carry if they were insulated in a conduit. No question. If you put bare conductor up in the air, for one, it's cooled through the air, and number two, it doesn't have insulation, so I care less about that conductor being hot because it's not going to melt anything. And number three, it's outside, so if it gets so hot, there's nothing outside on a pole. If you put it in a pole, nothing to burn. There's nothing to worry about. So if you put a conduit indoor or in a cable indoor, you worry about heat because it generates fire. Okay, so heat will dissipate through the insulation, as we all know, and into the pipe, wall, jacket, and cables or surrounding air. Heat is the enemy number one of electricity because it creates heat, melts insulation, it creates smoke, and eventually, if you're lucky, you create a short circuit and you trip before you burn the building. One thing about insulation, guys, what we love, I always say, we love, guys, copper. Copper, for example, here's your copper conductor right in here. And suppose this is my number 6 copper conductor. Number 6 copper conductor, no problem, Cu copper. So that's where the current is going to go through. Now, we need it to be very conductive, very great. And then, but also we want to insulate around that conductor because we want the voltage to go everywhere. So that's the insulation around it. So number is to carry the current, and the insulation that you're looking at here is number one is to hold the voltage. That's the reason why we have insulation. Otherwise, if you don't hold the voltage, you're going to have phase to ground volt, phase to phase volt, phase to phase to phase volt, short circuit, and so forth. Unfortunately, as you hold the volt, a product that we care less about is heat. You're only holding the voltage, but also you're holding the heat around that conductor. So long are great because they isolate the voltage, and that byproduct of them is also they hold the heat and get hot and they melt and so forth. That's the important thing, guys. If I carry the same current, will not damage their insulation if installed in a cool ambient temperature. So somebody down or air, my friend, if somebody tells you, for example, if I ask you, I have a 500 kcm 100 kcm, how much? Let's say THM, and how much current 500 kcm conductor can carry. And right there. Anybody can answer how much current a 500 kcm conductor can carry? Anybody can question? If I ask you how much current a 500 kcm conductor can carry, and stop. That's our Byron, my friend. Nobody. I don't know how much current a 500 kcm conductor can carry. I need to add the following. If I put a 500 kcm conductor in a conduit, now we're on conduit, ambient temperature, rated to an ambient temperature. What is it? The ambient temperature, they use 30 degrees or less. So if I ask you a 30 degrees Celsius, if I put 500 kcm in a conduit with another 3 hot conductors, ambient temperature of 30, and I'm going to land it on a log. Log is rated for a 75-degree column, right? That's what the conductor is going to land. Both these logs from both sides at 75-degree column. Look how specific degree Celsius the log. Then in a case like this, I'm sure you guys will come and say, "Oh, we know that for a fact. It's 380 amps." Can you get 380 amps? So for a 500 kcm conductor to carry 380 amps, first it has to be in an ambient temperature of 30, right? Then 30, but not 30, and the logs have to be 75. Then the conductor can carry 380 amps. So you see how much current a conductor can carry, guys. It doesn't anything. You have to put the circumstances for that particular conductor. So there is, again, the conductor can carry more current if the temperature is low. Why? Because if the temperature is low, guys, the effect of heating on the conductor is not going to be as substantial as if the ambient temperature is high. If the ambient temperature is high and you're heating the conductor will reach a melting point much higher than if it was in a freezer. How long you leave the conductor hot? The time is a big deal, guys. Also, continuous load or longer ambient temperature, extreme or more damage will occur. So again, if you put continuous load in an extreme temperature, you're going to damage the insulation much higher. Key point I want to give my friend, I want to which you guys come up with it, is a conductor can carry certain current based on the circumstances and the conditions. So if 500 kcm conductor, by the way, I ask you, Joe, the same 500 kcm conductor, if you put it in a cable tray, it's the same conductor in a cable tray, it will carry completely different amount of amps. It would not carry 380. You put the 500 kcm underground in a parallel circuit with 12 other ducts. It will be completely different amps. So the same conductor can carry different amps based on the configuration of that conductor. Here's a nice example. Suppose you have number 12, guys, the THHM conductor. Number 12 THHM conductor. 300 runs of it. Look at that. I put 100 in this temperature. That's Minnesota, minus 32 Fahrenheit. Watt and cooler. And another 100 in a 72. That's ambient temperature. I have another 100 in 150. Okay. Now, if you go after an example, after 5 years, I don't think any one of you have any doubt that the one inside the part that's one part, one conductor, here's another part, here's the third part. And so this one, the minus 32 here, and this is the 72. This one is the 150. I don't think any one of you guys have any doubt that the insulation right here will be damaged more than the insulation here and here. And why, my friend Joe? Of course, because the ambient temperature, 150 Fahrenheit, is extremely hot. It's going to make the insulation deteriorate much faster. Any questions about the effect of temperature on the insulation? Any questions? Now, my friend, if we don't have insulation, who cares? Have insulation. This conductor, if I have a power line, to a point, of course, not who cares. To a point, if I have a power line coming over here on the pole, and these are bare conductors like the utilities guys can have. These are my bare conductors. I have conductor up in the air, bare conductor. Okay, that conductor can carry probably, I would say, from 50% to 100% more, to 100 more, double the amount of current that the same conductor can carry if you put it in a conduit in a building. If you're in a conduit in a building. About conductors, guys, the single most important thing is the conductive material, copper or aluminum. That's how we carry the conductor. And the second single most important thing is the insulation, because the better the insulation, here's a catch-22, guys, Jacob. The better the insulation, the worse the heat, right? Insulate it more, then the heat will sit more inside. It wouldn't be dissipated, and of course, it will deteriorate the insulation. So that's catch-22. You need insulation to insulate the voltage, but at the same time, you are wrapping the conductor with a bit that the heat cannot dissipate. The heat that cannot dissipate. A couple of correction factors. Because of all of this, guys, we're going to be looking at correction factors based on the air temperature, using correction factor to determine conductor ampacity. That's what we're going to be doing. 3 conductors, phase wave, and duct banks. And duct banks, as you can see, I'll get to this one, this particular scenario later on. And suppose, do you guys remember 500 kcm? Suppose that this here was a 3 conductors in this duct, and each one was 500 kcm. 500 kcm. Okay, suppose that's the scenario that we have. I guarantee you that this conductor will not carry 380 amps. If this conductor 3 in a duct, in a configuration like that, it would not carry 380 amps. That particular one. So if you put the same conductor in a different configuration, it will get. This is, I'm sure, how many guys have worked with ducts like this? Ducts. And how many of you guys have worked in ducts? Like it will be 3. This will be 1, 2, 3 times 3, 9 circuits 500 kcm each, 9 circuits 500 kcm each, parallel circuits and so forth. Now this, then this conductor right in here is your weakest link, because I'm not going to tell you guys, because this is trapped, right? Can you guys see the trap? So the heat is going to be coming from all these ducts, and this one is trapped. All the heat are contributing from all these ducts, heating the block. This one here, it can heat further, right? Can you see the perimeter one? It dissipates here, heat faster. Anyway, so the worst scenario for this duct is going to be that one right in here. That's the one that's going to decide how much current the whole configuration is going to carry. We do this as engineering a lot with bus duct. You're paralleling a 4,000 amp switch gear, bus duct, underground duct from point A to point B. You have to have, I'll show you guys in a couple of other tables that probably some of you have never used, to find a conductor, how much 500 kcm can carry under these circumstances. Okay, any question, my friends? Any question? Any questions? Enough, then you can also calculate the ambient, the conductor, guys, based on different temperature. Based on different temperature. Get into that one. Okay, and you can find under engineering supervision. This is only under engineering supervision. You find how much current a conductor can carry. This, emphasize, guys, if you look at this, this is all temperature, variation in temperature, resistance of the conductor, the AC resistance. So D resistance. See effective thermal resistance between, that's the thermal resistance here. Then and the thermodynamic equation, believe not thermodynamic, has nothing to do with electrical. Based on the temperature, the resistance of the conductor, you can decide that a 500 kcm conductor, 500 kcm, I'm just under circumstances, let's say 160 degrees. Plug all these parameters, I can decide that this conductor can carry, let's say 300 amps under these circumstances. If you remember, guys, a long time ago, I think I told you there's a software that's called and Calc. Calc is a software that allows you to size the conductors the conductor can carry if you put them in an underground box. Suppose you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Each one of these here, each of them is carrying 3 conductors, and each one of these is 600 kcm. 100 K, C, and M. And let's put neutral here. Here's one neutral, and that neutral happens to be 400 kcm, and one neutral 400 kcm. Okay. So if you put them under these circumstances, it will tell you how much current a conductor of 600 kcm, the phases, will carry under these circumstances. So it's really cool software. For I think $1,000 or so, you can get it. Okay, so moving, my friends, into the foot care. Before I do that one and talk about this one, I'm going to go ahead and share my desktop and just review things in terms of conductors you can't go without. You can't go without. So I'm going to go ahead and share my desktop, and I want you guys to take some notes on that one. Share job. Okay, here you go. I'll directly guys into a few things here. Here's the, by the way, they in 2014 and 2011 they changed it slightly, not a whole lot. So the article that talks about ampacity for conductors, as we all know, guys, is right in here. Let me go see if I can get feedback. It's there. You can see back here. All right, and it's always chat here. So okay, your chat. Okay, so let's go ahead and go over a few things here. 3.15, my friend. 3.15 is, please, if you don't know that, please take a few notes here. If you don't know how to use it, it's tough to go ahead. So if I have more than 3 current conductors, guys, I can derate. So if I have up to 6 conductors, I can cut them by 80%. If I have up to more than 41 conductors in a raceway, you can cut by 35%. What does that mean? So a very quick example. Suppose I have a conductor, and this conductor was supposed to carry 100 amps, right? If I put this conductor under these circumstances, it put let's say 40 of these conductors, one conduit. You will take the 100 and multiply it by 440. It's 0.4. 0.4. That's what your beautiful 40 amp conductor now is carrying nothing but 40 amps. Okay. Question is how to use this table. Any question about how to use this table before I move on to the next table? And this table over the next 4 chats. Everyone knows how to find the response, guys. There you go. So that's how we use this table. No gimmicks, nothing. Second table, guys. This came in 2008. This particular table. If you put a conduit on exposed to the sun on or above the roof, it was a conduit or above the roof exposed to the sun, and both I decided to put it 3 feet, right? 3 feet. They have to add 25 degrees Fahrenheit. So this is just the ambient temperature for here's my conduit right in here. Ambient temperature for this conduit was 90 degrees Fahrenheit, right? And I single-handedly Chad Curdy to go install this baby here. I put it here on some type of a support and pull my conduit, and my support was let's say it was 25 inches. 25 inches, okay? 25 inches. Then ambient temperature, guys, for this situation, Let me just go grab another. So then the ambient temperature becomes, add, in this case, 25. So all of a sudden, you found yourself in a temperature 150 degrees Fahrenheit, and you rate based on 150 degrees Fahrenheit. I ask you if anybody has any questions how to use this table, guys. This will add a temperature. This will be on your journeyman exam. No question asked in my mind. How to add a temperature based on how you put the conduit above the roof or above the roof. Any question how to use this one? Any of my friends how to use it? Oh. All right. These are the two tables that I want to mention quick on that one. Moving on, so we know how to use these two tables before we move on. Okay. Conductors, I'll emphasize this table, guys, as basically for residential. So I always want to highlight, make sure if you're doing residential, is 12240. It has to be 3-wire. It's single phase. It's one services and feeders only. So this table, if you have, suppose I have a panel, guys, here's my panel. My overcurrent detection device in this panel right here. Let's just say it was a 400 amp, and then you find a conductor that can feed this panel. Conductor. Here's my 400 amp, and I am listed in a cover company, so that will be 400 kcm. 400 kcm. So my friend, somebody else decided to go, okay, well, Chad, I'm going to use aluminum, right? I don't care copper, I'm going to use aluminum. So if you use aluminum, then you're going to have 600. I have 600 kcm. 600 kcm. So these is, so that will be your two hots, basically. Your neutral, either you go the full neutral and make them 3. Or you can go 1-2 steps below, or you do the neutral calculation. There's a neutral calculation. So the practical reasons, let's say here's my 3 conductors, 100 kcm cover, or 3 conductors. These are single phase. Remember, 2 hots and a neutral. 3 conductors, 2 hots and a neutral, 60 kcm alone. Okay. May I ask you any question, guys, how to use this table? And to use this table, you need to know how to use this table. Okay. If you don't care, under only engineering supervision, so you have to have engineering supervision. Under engineering supervision, conductors, it shall be permitted to be calculated by means of the following formula. So I, as a registered engineer, decided to go the hell with that 400 kcm. I want to use my engineering formula to come up with different numbers. Can I do that? Absolutely. Engineering supervision, my friends, I can make, I would do, I make number 14, I'm going to exaggerate here, number 14 carry 35 amps. If I calculation that proves it's not going to heat up based on this formula. I'm exaggerating here with number 14. The formula, guys, and you wouldn't use it unless you're familiar with it, unless you have a software that does with it. It's all about temperature. So conductor temperature in degrees, ambient temperature in degrees, dielectric loss temperature, DC resistance at the temperature, component AC resistance resulting from a skin effect and proximity effect, how close to each other, a fixed thermal resistance between conductors and surrounding the temperature. So you can see how these basically a thermodynamic equation that you're looking at. That won't have to worry too much about them. I'm not sure about this, but at least know if you ever see something, and my friend Gerald, and it doesn't make sense from your experience, just remember, if it's done under engineering supervision, you hope those fellow engineers know what they're doing and they use this formula right. So you can use this formula under engineering supervision. Different amps than 310-16. Okay, the single most important table in the NEC code book, as you guys know, this is the most important table. 310-16 And plus 16, I know I wrote this one. I will write it one more time, and I will give you a break. I know you guys are due for a break. So let me write the rules for using this table, and I hope you listen to Chad and you do it one time. Okay, now how to use this table? How this table? I'm going to write a few things, guys, for you here, and I hope you will listen to me. First of all, I want to start with the 60-degree column. Here's where you use the 60-degree column. Number one, guys, if you don't know anything, if amp is equal or less than 100 amps. If you don't think and the amp is equal or less than 100 amps, you always default to 60-degree column. No question asked. Conductors 100 or less. Number two, the insulation, I'm going to say N or insulation is equal or you can use how am I going to say that? Equal or less to 60-degree column. If your insulation is rated to 60-degree column or less, this is degree Celsius, you have to use the 60-degree column. Okay? And the last one, if your conductor is equal or less to number 1, right in here. If your conductor is equal or less to number 1. Number 1. Any question about these rules? That's basically your default. If I know anything, then I don't know anything about the system, and I see 100 amp panel, I go size it based on 60-degree column. If I don't know anything and I see a conductor number 2, I go and size the conductor number 2 based on 60-degree column. Any question about that one? So what I would do, so basically these conductors, which is these ones from here up, they directly, you got this, guys, it's go right here with the 60-degree column. They have to be, I can't emphasize, they have to be not more than 3 carrying conductors in temperature of 30 degrees, and it has to be not the voltage up to this voltage and all this good stuff. All things considered. Question there is about this, how to use the 60-degree column. Any math, any questions? Okay, let me go and write the other one, the 75-degree column. The 5-degree column, guys, is the same rule, almost the same rule. I'm going to go ahead and write them in a different color. I'm talking about the 75-degree column. Number one, let's look at the current. If your current is more than 100, then no problem. You're going to default to the 75-degree column. Insulation, IN stands for insulation. If your insulation is more equal, insulation is more or equal to 75-degree column, then if your is more equal to 75-degree column, then you're gonna default to the 75. Okay. And last one is conductor. If your conductor is more than number 1 conductor. Okay. Let me show you a few little things here. Tricky thing. If I go here and my conductors, these conductors, guys, are more than number right. All the S, all down. Go directly from here. It goes all the way. If I don't know anything, okay. See how it goes with the 75. And last one I like to do, guys, is also motors. Default, if they're motors, you go default to 75. These are the 3 rules for the 75. The current is more than 100. The insulation is more or equal to 75. If the conductor is more than 1, and it's motors. Any questions about this? Any question about defaulting? Any question about defaulting? Question would be then, and by the way, I should probably should correct this one right here. Can you get corrected here? Then be insulation. Insulation is more or equal to 60. More or equal to 60. equal to 60 to use this column. Can you guys see? I'm going to highlight a different color, the one that I corrected here, right in here. The question would be then, Chad, when would we use a 90-degree column? The 90-degree column, guys, to use the 90-degree column, number one, I'm going to write it right here. Number one, insulation can be more equal or more than 90 degrees, right? If it's not equal or more than 90 degrees Celsius, don't even think about it. So that's rule number one. Number two, you use it only for derating. You can see that for derating. You will never ever, my friend, you never ever size based on the 90-degree column. You always use it for derating. Always use it for derating. Always use it for derating. And I'm showing the aluminum here, the cover, but the aluminum, these two, the aluminum is the same. This one, as you guys know, this is aluminum, and this is for cover. This is for cover or aluminum. Guys, about the three columns. When do we use the three columns? When do we use a three columns? And about the three columns, when do you use the three columns? They tell you otherwise. They tell you otherwise. Okay. So let me give you a quick example. Suppose I have number 4. Number conductor is coming over here and tied to a log. Is my log. Current can number 4, and it's 3 conductors. 3 of them. There is current conductors in a conduit feeding a motor. Here's my motor through a log. A motor. Let's feeding a machine. Not the machine that welds or machine that machine. Feeding. How much number 6 can carry under these circumstances? Guys? Temperature is the same. I mentioned that it's number 6 conductor right in here. Can you guys see that? Number 6 conductor goes with 55. So it's 55 amps. No question. Amps. Now suppose this conductor, guys, is feeding a motor. The same conductor feeding a motor. The same conductor carry a 65 amps. 65 amps. Same conductor, I can load it to 65 amps. It would be, Matthew, what the heck are you talking about, Chad? 65 from 55? Yeah, 65 by 65 because motors, guys, have overload protection in them. It will be protected, 65. Okay, that's where the motors are, 65. Now, let's take a quick other example, guys. Suppose I have a panel, in the panel right in here, and the panel happens to be a 400 amp, panel. Okay, how much can a 400 amp panel carry under these circumstances? Let's look at the one. You guys agree with me? This will be rule 75 because it's more than 100. Okay, I need 45. I need 40 amp panel. 40 amp panel. Well, the cool is I can use 100. I can use 500. 5 ACM. KCM. Now I'm sure some of you guys are looking at me and say, Chad, but look at 500 can only carry 380. They use this because the next overcurrent protection device is 400. That's okay. In a case like this, so the current is 380, but the 400 amp, is this okay? Yes. Yes. If it's based on rules in the code that says if the overcurrent protection device is the next standard, then no problem. What's the next standard overcurrent protection device? 400. 80, it's 400, right? So that's okay. And yourself 500 KCM. So, but where did I go? I went to the 75. I went to 75. Any questions? Any questions? Eric, my friend, Jake, Gerald, Joel, Matthew. Okay, basically what I can emphasize, guys, if you don't know rules, you'll you'll find a hard time. You'll find understanding this table. Really a hard time. And all these, I'm going to go get rid of this one. Okay. And a couple of things, and I will do for a break. Just bear with me 1 second here. I will bring to your attention, guys, the small conductor rule. There is a small conductor rule that says, small conductor rule, no matter what your calculation is, number 14 cannot carry more than 20 amps. Number 12 cannot carry more than 25 amps. And number cannot carry more than 30 amps. And by the way, they changed these in 2011. I believe 14 now is 15 amps. And they changed this one slightly. And this is actually 14, 15, 20, and 30. So these conductors, guys, no matter what you come up with, this is led by code to 50 amps, and this one to 20 amps, and the third one is to 30 amps. So no matter what your calculation came up with, use a small conductor rule for only these three conductors, only for these three conductors. No matter what you come up with, you have to stick with 15, 20, 30. There's some option with motors, but that's a small conductor rule. Factors, and let you guys go with that. I want to bring to your attention, guys, if the ambient temperature is different, just quick how to use this factor here. Suppose that we have an ambient temperature of, let's see, Fahrenheit, an ambient temperature right in Arizona, and it's 140. And suppose I, Chad Curdy, decided to use a THSN conductor. Is a THSN conductor, so it's for 90 degrees. And I need to derate, and my derating factor is 0.7. See that? Now, suppose my friend Joe decided, he said, Chad, I hate the guts of THSN conductors, and I will never use a THSN conductor, okay? And I'm going to use an E conductor, right? I just decided to use a USE. Is there a problem with that? A USE conductor. Then if you are to use a USE, well, guess what? Now you are down to 0.58. If you need to use a US conductor. They don't want you, if you guys look here, they don't want you to use even a 60-degree column. There is no number for it. It's a money, basically, to use it. There's nothing here for it. So that's how, if you use a THSN conductor, your insulation, your derating is 0.58. 71. If you use a THSN conductor, that we use THSN conductor all the time. THSN, THW. Any question about how to find the derating factor based on the insulation? Derating factor based on the insulation. Factor based on the insulation. Let's take one more quick example. Suppose we have, let's say 105. Suppose I'm using aluminum. Here's my aluminum conductor. I'm using, let's say I'm using this insulation, XHW-2. Okay, the rating factor, because the conductor is 0.87. Now, friend Matthew decided, he said, Chad, I don't like this type of insulation that you're using, and I'm going to use this insulation, XHW, in a wet location. Let's say, and it's in a wet location. Because look at that, guys, XHW in the two locations, right? If you use it in wet location, it's 75. If you use it in dry location, it's 90. So suppose you use XHW in wet location, then my rating factor is 0.8. I have my friend Eric decided to say, I don't like what you guys have picked, and I'm going to use, I love TW, and I can't live without it. I'm going to use a TW insulation. And what his rating factor is 0.71. Can you guess, based on the insulation, you come up with a different derating factor? Now, which one do you think more economical to use if the temperature is I have a very high temperature like this? Of course, to use an XHSW-2. XHSW-2, that was the best application because you can get amps. You can get, just to get you an idea, if I had 100 amps, look, just assume the conductor was carrying 100 amps. Based on the first, you get 87 amps out of it. Based on the second, you get 82 amps out of it. And on the third, if you use it, you get 71 amps. Now you get little amps from the conductor. Besides the conductor, what do? You get bigger conductors. You get bigger conductors. Who cares about bigger conductors? You can spend money for the same project. More money for the same project. Okay, one more time. Any questions? Any questions about how to use that? Any question about how to use this table? I can't emphasize how important to use rating factors, guys. I'll get back to this. I'm gonna go give you guys a quick break here. Go back. Let's take a quick break, my friends. Is it here? 10. Let's stay at 7:16. Let's back at 7:16 p.m. Okay. Thank you. Can we get back? May I give you back, guys? Check in. Thank you, my friends. Time flies. Let's go ahead, guys, and I'm going to go one more time, share my desktop. I will show you a very interesting table that you can literally live without. And this table, my friend, is right in here. This have changed in 2011, changed the name, not the content. This is one thing of the most important tables in the NEC code book, guys. And let me just let you guys and grab you here so I can see your response and your. Okay. Grab your chat too. Okay, second here to set my. Okay, you guys look at this table. This installation type of every type of approved method in the NEC code book. Let's start with a cable. If you guys using a mic cable, if you use it in a dry and wet location, 90 degree no problem. With special permission, it can go as high as 250. Okay, use a mic cable. Check your left. Let's look at that. RHH. It's thermostat. It's rated for 90 degree in a dry and damp location. And let me just move me up here. Damp location. Where you find the installation, let's go THH. Okay, here you go. Grab this one. So again, RHH, you can only use it in dry damp location. It's rated for 90 degree. If I use let's say SA cable. SA cable rated for 90 degree, but remember, dry or damp location. Special, I can't use it in wet location. It can be rated as high as 200. So these are SIS cable is rated for 90 degrees. TPS rated for 90 degrees, which is switch wiring. This tells you what and I don't know if you guys look over here. It will tell you what the insulation type is, what the size that you can buy it from, the circular rail, as well as other covering if it has any other covering. This is the most important, as I say, cables that you're going to encounter in your career. Let's look at this one, guys. TSH, you guys remember TSH? TSH is on a dry or damp location, rated 90 degree. Why it's 90 degree? Because it says this table says so. This guy, look at this, guys. It's TSHW. If you use it in a wet location, it's 75. That's how they catch you on the test. If you use it in a dry location, it's actually rated for 90 degrees. So if you use it in a wet location, 75. If you use it in a dry location, 90 degrees. Right? Look at this one, guys. The same thing. TSW, 75 degrees, damp or wet location, 90 degree, only special permission. This guy, 90 degree, dry or wet location. Bring it on. Look at this one, PHD-N, 90 degree, dry or wet. If it has a 2, it's 75. W, it's only 60. Don't even think about it. UF, it's only 60. Don't even think about it. What tells you guys what the insulation is rated for based on the application? One interesting one is this baby here, X here, XSW-2. It's 90 degrees, dry or wet. Bring it on, no problem. If you have a ZW 75 wet location, you can have 90 degrees for dry with a special permission. This is wet and damp location. Wet location, dry and damp location. Special permission. So you can see, guys, here if you use ZW-2, 90 degrees, dry and wet location, no problem. Dry, wet location, dry and wet location. Question, guys? Any comments about how to use this table? Any question? Any comments about how to use this table? Any comments? And this is where you can, especially, guys, this insulation here. I always trick you with that because it's always rated for dry location 90 degrees, and then get you this insulation XHW-2. It's 90 only if it's dry and damp, and if it's a wet, it's actually 75 for wet. 75 for wet. They trick you on the German exam, that particular one. Okay. basically how to use the table, the rating. We'll take a few examples, guys. So before a few examples, guys, I'm going to go. So here's how we size. Let me tell you how we size conductors for any system. Two ways we size conductor. Base and it's continuous. If it's continuous, continuous. If I can spell that one. Number two, based on durating. Do I need to durate? Is there durating factors based on rating? Okay, durating. Number three, my friend, is based on voltage. Oh, makes a sense, huh? So what we do, guys, is when we size a conductor, you have to take into consideration the following. Number one, is the load continuous? If it's continuous, you have to multiply by 1.25, right? That's how we size continuous loads. That's one. Then, do I have to durate? Is there factors involved? If yes, you have to durate. Voltage drop. Do I have to do voltage drop? Is there longer distances? Am I running 100 feet or more that I have to pay attention to voltage drop? Then I have to rate based on voltage drop. So this guy, when you size based on continuous load, you came up with 4 odds. So when you do it, you came up with 2 odds for the load. And suppose when you did a voltage drop calculation, you came up with 3 odds. Okay? Same amount of load. Can you see that? Calculation, 3 different separate calculations came up with 3 different answers. Which one you suppose that I have to pick for my circuit? Anybody can have any idea? I came up with 4, 2 odds, 3 odds. Which one can you check with me? Highlight on my screen, the one that I should use. You guys can have my screen too. Which cable I'm supposed to use if I did 3 calculations? One of them came up with 4 odds, 1 2 odds, 1 3 odds. Which calculation am I supposed to use? Safest. Look at it from a safest point of view, guys. Which one? The conductor, the safer the conductor, right? Does that give an idea? Okay, so the insulation, my friends, I'm waiting for you guys to tell me that. The insulation that I must use is the largest, the conductor is the largest conductor. No question asked. You do 3 calculations, the largest conductor you have to use, because the safest. So you guys to keep this in mind as we go through. The conductor, this talks about, guys, the foot, the section area. There is, when we size based on voltage drop, I want you guys to highlight a few things here. The most important thing that that I highlight is there is a formula that says, okay, let's use a different color here. For voltage drop, it is voltage drop. Voltage drop equals K. Well, based on this one, Ki over Cm. This important formula, guys, that you size, you find the voltage drop for the conductor. And I'm sure a lot of you guys seen this one. The K, here's what the K stands for. K is the resistivity in ohms per circular mile, and in feet, not meters. R, I don't have an R, but R is the resistance of the cable, and Cm is the cross-section area of the conductor. The cross-section area of the conductor. Find the voltage drop. Suppose I don't care about the voltage drop. Suppose I want to find the conductor, right? I find the conductor. If I flip this formula, Cm equals Ki and F over voltage drop, and we size conductors based on voltage drop. Exact formula. Then we size the conductor based on the voltage drop. If you look at the circular mile, K is the constant right here, then 10 point copper, or 12 ohm, or something, or 17 ohm. And how far the figure is. Circular L is the cross-section area of the conductor, and R will not here, but R, if we have it, it's going to be the resistance. Anything guys about this formula? Any question about this formula? Any about this formula? We'll take a few examples about it in a second. Tells you guys, I'm going to go back to this example. What tells you is this one here at the top. Tell you the resistance of the conductor is a function of K, which is the neural phenomena for that particular conductor material, like copper or aluminum. Multiply the length, divide by the cross-section area of the conductor. What does that mean, guys? It means the longer the conductor, the more resistance. The size of conductor, the smaller the resistance, and it stays constant for all types of stay constant based on temperature. That particular insulation, copper or aluminum. These, as you can see, three forms of the same thing, basically three forms of the same thing. There's the two formulas that dear to my heart. I would like you guys to write them and maybe because they will be your exam. Number one is size of conductor, circular mil, as I wrote it before, equal L K K is, and we L is the length, I is the current, K is the constant related to the type of the material, divided by the voltage drop in volts. Second one, guys, is over CR. Let me write it down here for voltage drop equal R I N over 1,000 over 1. The one that we use, and this one here so I can flip it. The second one is the resistance, R equal voltage drop times 1,000 divided by if you flip this one, divide I the length. These formulas are the single most important formulas when it comes to sizing conductors based on voltage drop. Conductors based on voltage drop. Single most. They're supposed to give you guys the same answer. Now, suppose, my friends, this is a single. These are for single phase. These are single phase. Suppose you three-phase load. All what you have to do, and I'm gonna go grab my. All you have to do if it's three-phase is multiply this side here by 1. No, it should be the 1.73 here. Just gonna see where it's gonna go. Right here. So it's gonna be 1.73 right here and 1.73. What you have to do is multiply it by 1.73. If you multiply it by 1.73, that will be a three-phase load or three-phase loads. What do you guys about these two very important formulas to size based on voltage drop? Any more math to my friend Ross? Questions? Now you find the R, table number 8, guys. The DC resistance can give you DC resistance for all the gauge approved by NEC book. It's in turn 9. We'll check into that one in a second. But the most important thing is knowing these formulas. Circular mil equal. How many of you guys have used these formulas before? How have you used these formulas? Green check, seen them or used them? Anybody? Green check, X, no. Green check if you have used them or seen them. Circular mil, don't be embarrassed, no problem. Circular mil equal KL over the voltage drop, and equal voltage drop times 1,000. And okay, we'll take a few examples, guys, just to explain it, but I want you guys to keep these in mind. So if you know that the longer the distance, higher the voltage drop, the bigger the conductor, of course. If sizing, it makes sense. If I'm sizing a 500 kcm and I wanted to carry 380 amps, the 380 amps I can carry them for a certain amount of distance. If I wish to go longer, then either the amps have to go lower, or because the conductor stays the same. So the amps basically have to go lower. So there's a calculation that we can do to find the amp, the conductor, the length, and so forth. There's concept, and I will get back to these rules. Please write them down because I will use them in a few seconds. If you don't know now, the circular mel, which is an interesting phenomenon, the mel, I don't know if you guys know, mel is actually 1,000th of an inch. 1,000th of an inch. You have a circular mel because that's how we measure in the U.S. the cross-section area. Circular meaning a mel squared, a mel times a mel. Is a mel times a mel. That's a circular mel. So if you 0.001 multiply it by 0.001, that will give you a circular mel, basically. That's a mel. Any this quick example to understand what a mel is. So we have, and it's actually the diameter. The mel is the diameter of the conductor. Suppose I have a conductor. Here's my conductor. I'm going to exaggerate here. And the diameter of this conductor right in here is actually 0.1 inch. So 0.1 inch, my friend. 0.1 inch. If you would have, okay, so if you convert the 0.1 inch into mils, you basically divide by 1,000. Divide this by 1,000 or change it into 1,000. That will give you 100 mils, right? Because 100 by 1,000 gives you 0.1. 1,000 with 100, take a 0.1. I want to put this one into something. The bar is 1,000. Think of this way. I know that's what the mil is. So how do you make a 0.1 to 1,000? So as you can see, this is 100, right? Basically by 1,000 or more by 1,000. So that's 100 mil. Okay, so if you take 100 mil and you square it, take 100 times 100, that will give you 10,000 circular mil. 10,000 circular mil. Here's what we care. If you guys can see, when I say a 500 kcm, remember the 500 kcm. Okay, so 500 kcm, right? That's a very common one. So this means it's a 5,000 cm, right? cm. So if you want to find in mils, what's the cross-section area in mils for this? Take the square root of this. You take 5,000, 500, 1,000, 1, 2, 3, and take the square root of this. Oh shit, square root. You can get 7. This is mil, M-I-L. This is now mil meaning nothing. If you so 707 mil. All what it is, guys, is just take the square root of this number. Square root of this number. That will get you 707. Now divide this 707.7 divided by 1,000 to get actual inch. That gives you a point, as you can see, 0.707 inch. So I put the inch sign here. 7.7 inch. Okay, so that's the diameter of a conductor. That's 500 kcm conductor. The diameter of 700 kcm conductor. Any questions about this? How to find the diameter? And you can find them approximate diameter. Any question about how to find means? Please don't ask you this question, of course, but it's really nice to understand where the 500 kcm came to be. 500 kcm, 2,000 kcm. 2,000, you take the square root of it, that will get you the mil, the diameter of the conductor in mil, divided by 100. I'm sorry, 1,000, that will get you the diameter in inches. The diameter in inches for that particular conductor. Okay. So, okay, so for now, conductors. Let's take example. Guys, sizing examples. So do me a favor, grab your code book and make sure go to table 310.16. Let's go to table 310.16. 16. And 3 stainless 16, I have a cable, a conductor, and this machine is this is my three-phase machine, right? And here's my conductor going feeding it. And this machine, let's suppose that we have a three-phase, it's 3 conductors. Oops, let's go. So let's just say conductors feeding this machine, and each one of these conductors, let's say each one of these conductor is 4 odd. Okay. For the ambient temperature, the temperature that this machine, my friends, the temperature is this machine at, as let's see 130 degrees Fahrenheit. The insulation that this machine is wired with is THH. Okay, so we have a 4 aught THH conductor, and temperature is 130 degrees. A temperature is 130 degrees. My question for you, my friends, is we need to find how much current can this machine how much current can this machine carry under these circumstances? That's the question. How much this machine can carry under these circumstances? Okay, let's go together. Let's start with the duration. I want you guys to take the, let me just use a smaller here. Let's take 4 aught. Take the 310.16, right? 310.16. And either way, what type of if you know what it is, it's always copper, right? It's a cover. Go to 310.16, and since the insulation is THH, so I have to go to the 90-degree column. 90-degree column. Why they go to 90-degree column, guys? It's a THM. The insulation THM. You guys go to 4 aught cover under 90-degree, 4 aught cover under 90-degree, 260. Can you get that? Everybody can see that? Can you guys acknowledge that everybody can see that? This one, please. Can you green check saying that yes, Chad, we see that 4 aught under 90-degree THH can give you 260, and you're not, huh? Okay, so that's basically my THH. The second step, my friends, is my second step is to take the, here's step number 1 here. Step 2 is to take 260 based on the same thing, table 310.16, and based on the ambient temperature or 130 degrees Fahrenheit. I take this one based on 130 degree Fahrenheit, guys. If you go cross-referencing it, your rating factor is 130 is 0.76. This, my rating factor is actually 0.76 times 200. Can you guys see that? Anybody disagree with that? So based on 130 degree, my Fahrenheit is 0.76. And if you do your calculator handy, 260 times 0.76 equal, I have 198. Give or take 198 amps. 198 amps. Any question about how to do it? Any questions? So we cut it by 0.75. Everybody knows, guys. Everybody knows how to find a 0.75. Cut it by 260. Okay. Now, am I done, guys? The question is, am I done? No. Here's what a lot of people don't understand. Then you guys to take the 4 aught. And the last one step is, I call it the check step. And 4 aught, guys, under normal condition, what's the normal condition for 4 aught? 75 degree column. The 75 degree column, that's a normal condition for 4 aught. 230 can carry 30 amps. Okay, condition. Now I exceed due to normal condition for us. Now, because of the circumstances, it can only carry 190. You need to check, guys. That's called a check. Check at the end. Can I exceed what number for watt can carry under normal condition? No. So suppose that suppose guys 198 was more than 230. Suppose the 198, the number I calculated was more than 230. Then your cutoff must be, Eric, my friend, 230. 130. And about this one, I call this last step is check. You need on calculation. You need to check. Says about this. A lot of steps, the last one, the red one, guys, a lot of people forget that one. A lot of people forget that check. You need to check before. My conductor, that load cannot be more than 108. The load cannot be more than 198 F based on these circumstances. Circumstances. Any question about this? How do you rate for a conductor? Now I'll make it more interesting, and I'm going to go add a voltage drop calculation right at the same problem. Suppose from here to here that this was 300 feet. Conductor 300 feet, cover conductor, and it's 300 feet. Okay, and I need to find I need to size the voltage drop. Now the first size, remember guys, the first size we came up, the first amp that we have is 198. I need to see how much current can I take out of this conductor under these circumstances. And with this, everybody knows what I'm doing right now. This time I will find how many currents can I get out of the 4-aught if I am to pull the 4-aught 300 feet. And this, I need to give you the voltage, guys. It's 3-phase, and the voltage is 480. The voltage to give you the voltage. If I want based on voltage drop, I have to give you the voltage. 480. Let's go do that. So we need to find the current. So you give us the formula that I gave you. I said the formula always remember is voltage drop equal 173 times K and divide this by circular mile. Okay. Now they're asking us, guys, how much current. I want to find the current. I know about you guys, but if I flip the formula, it becomes voltage drop multiplied by the circular mile and divided, that's multiplied by I, which is 1.73. I hope this is second nature to you guys. K and you flip the formula to solve for I, right? What bottom with I goes on the top on the other side of the equation. What's on the top with I goes on the bottom of the other side. Can you just see that this was at the bottom? It top here, and these two up, so they have to go at the bottom, right? That's end up with voltage. This is why the voltage drop approved by the code guys. The voltage drop problem, as you know, 3% on feeders. So 3% by code recommendation. So voltage drop 3% means 0.03. Where do they get the 0.03? 3% on feeders. Multiply what's the voltage? 480, right? 480 multiply by the CM. We'll get back to the CM, guys. I'm going to go back down to 1.73 here. 1.73 times what's K? K is 10.4 based on the book that we have. 10.4. It is 300 feet one way. 300 feet one way. Last piece that I'm going to do right here, guys. It's the circular mill for 4/0, right? My equation was 4/0. Was which one was it? Here we go. It was a 4/0. You guys it was a 4/0. So I'm going to go from table number chapter 9, table 8. From 9, guys, table 8, you can find chapter 9, table 8. You're going to find the circular mill as 211600. 211600. Everybody got the 211600, guys, circular mill? This is circular mill for 4/0. Remember that? That is the circular mill for from chapter 9 till number 8. Here's how we came up with these. Let's have a note. Chapter 9, table number 8, not number 6. Table number 8. Question, guys. Chapter 9, table 8. Circle mill for 4/0 is actually 211600 circle mill. Question about that. So if you have a good calculator, guys, go ahead and plug these and get me what you have. 0.03 times 480 times 21100 equal divide open brackets 1.73 10.4 times 3 close the brackets equal doesn't circle. Okay, over some, so voltage drop, we got 300. I have the numbers. How anybody, can you guys do the calculation and tell me what you came up with? I'm just curious to see what you came up with. You can do that and give me the what you came up with for 21160. Okay, no, it's 0.03. I think it's 0.03 times 480 times 21160 equal 70 times 1.2 times. Okay. Anybody can come up with something, guys? Come up with that you can carry. Anybody? Okay. Circle 11 by L by L. Okay. Any come up with 0.3. Okay. That's about. I'm coming with a number that's interesting. 0.7310 300. Yeah. With this number, I don't know if you guys came up with this 565 amps. 55 amps. Anybody came up with something different, guys? And I remind you what we came up with before. 198. So what we're doing here. So what okay, let's see if it doesn't make sense. Number is too high. Okay, 1.7, no. KIL over CM, okay. We need current, so CM times voltage drop divided by 1.73 KL. Okay, anyone with something different, guys? Can you chat with me? Do you have your handy? So that's the number that we came up with. If this is a number that, if my calculator is awake, I can't use this number. I can't use this number for whatever reason, because I can't exceed what the conductor is rated for. Where did it go? I can't try to find which whiteboard that we did. Okay. No. Just here. All right. Now this. Okay, there you go. I choose you guys because the amp that we with was with was 188. Like, I don't know why we came up with this high amp if we're missing here. I need something different. Can you guys share it with me? Make sure not 0.03 times 480. 0.03 times 480. Calculator is leaving times 2.1600 equal divide. Open the brackets. 1.3 times 10.4 times 300 close brackets. No, it's the same number. I came up with something different. Joe, man, Matthew, where are you guys? No? Any calculation, right? Because you came up with a number like this, obviously it's a very huge number, so you can't use this number. You're stuck with whatever number. That's what you guys come up with sometimes when you do the voltage drop calculation, especially at the high voltage. I want to emphasize, guys, the voltage that we are using here is a very high voltage, as you can see. You end up with an amp that you cannot, doesn't make sense. You can't use it. You still have to adhere to the rules, which is you can't create here the minimum amount of amps if you are to do it, and if you are not to do it. That's what I came up with, my friend. And 230. So if you guys came up with something 4-out cannot, shall not, will not carry more than 230 no matter what. So if you came up with something weird like 565 amps, you can't use it because you still have limited to 230 amps or less, 230 amp or less. So anyway, I thought that was the example was off the wall, but it really emphasized the point. You can't use 565 amps the same way you can't use it because conductor is limited to 230 under no more than 230. Guys, any questions? So the key point is when you start conductors, you choose the conductor, the amps of the conductor, the smallest amps or the largest conductor size, the smallest amps or the largest conductor size. Something more. Let's do this way. Let's put it this way. Let me have those guys here and go a voltage drop calculation. The voltage was a 500 feet. 500 feet, and I use a 400 kcm. 400 kcm. No, I want to size the conduit. Let's go size the conductors. Let's just say. Let's go table and find the amps that I have an amp, a load 100 amps. It's just 100 amp load. Load, guys, non-continuous 100 amp loads. If I have to size 100 amp loads in the distance from here to here, let's say 5 feet. The distance from here is 500 feet. And the voltage is 208 3-phase. 208 3-phase. And this is it. Okay. My circuit needs to size the conductor based on these circumstances. Okay, go ahead, guys, and circular mel equal 1.73 times K I L over voltage drop. So that conductors. Let's just go quick and the math. 1.73. It's so the K is 10.4, and it's going to be carried as 100 amp, and the voltage drop is actually 0.03 times the 208 because 3-phase. 208. Okay, do the math for me. I'll do a calculation and see if we come up with an answer. So 1.73 times 10.4 times 100 equal, divide this by 0.03 times 208 close the brackets, and equal. I come up here, I go with 288 and 88. 200. Anybody something different? Circular mel, circle. Anybody something different? I think I have a feeling that my calculator is 200. Okay. Volt to kill. Over CM 1.73 volt drop 1.03 100 amp 1.7310 K. Oh, dang! That's why it's out of whack. That's why it's 500. Chad, duh. So you have 1.73 times 10.4 times times 500 equal. Divide this by 0.03 times 208 equal. So it's more like it. It's that's more like it. And we grab the number. There you go. And grab it, and you end up with a number that's 144. How many is 1441? 167. Okay, 144,167 circular mil. I don't know about you guys, but if you take this one to know what size is there, take this way to chapter 9, 8, so you can translate this language into something that we understand. Okay. And if you guys go to 144, I have 167, 133, 144. I need 144, 133, 167. That's 3 aught. It'll translate, guys, into 3 aught. 3 aught. AWG. AWG. So on the voltage drop problem, my friend Juan, I need a 3 aught. 3 aught. Based on the drop problem. Now, if you size this one, guys, without a voltage drop, just as 100 amp non-continuous, you size it just based on 100 amp, and you take this one to 3.16 and set 100 less, you go to 60 degree column. You go to degree column. If you go to this one, what would that be? Number 1. If you go to this, that will get you number 1. Will get you number 1. Number 1. So emphasize, guys, based on the voltage drop calculation, you came up with 3 aught. The actual sizing, no derating, nothing, you came up, as we can see, with number 1, right? This is the degree column, and this is, we came up with 3 aught. Which conductor do you think we're going to be using? Which conductor do you think we're going to be using? We're going to be 3 aught. Everybody agree with that, guys? 3 aught, the largest conductor based on these circumstances. Agree with 3 aught. So exercise, guys, when you do voltage drop calculation, and you do good load and you do derating, you're going to pick up the conductor that gives you the largest size, or the conductor that gets you, if you're sizing conductor, you're going to pick up the largest size conductor based on drop or based on or basic. Asking guys about this problem, any question? Any? So if you guys are, I did number 1, I sized based on 100 amp, and number 2, I sized based on circular mil, and I picked up the size. As you can see, the size that can get me the largest conductor. So I use the aught. I'm sorry, I have to use the 3 aught. What am I saying, Chad? Here, I picked the conductor. There you go. Okay, grab this one. There you go. Picked up the 3 conductor. because the largest conductor. So I wouldn't use that number 1. We are. Any question is any question about sizing based on voltage drop and sizing based on sizing based on the rating. So that's basic all these tables. So that's based on the rating. Let me see what we have here. All right, I'll give you a quick break here, and then we'll continue. What time is it? 8. Let's get it. 801, 802, 808. Let's go 08 p.m. 08, and then we'll continue p.m. Okay. Yes, you can check in, please. Thank you, my friends. Let's go ahead and start. Okay, so basically, what I want to show you the voltage drop calculation, guys. Can't emphasize when you size conductor, you size it based continuous loads first, then based on the rating second, and based on voltage drop, and third, and you choose the one that gets you the largest conductor. Okay, so another thing that that you have to pay attention is to when you put conductors, you have to put them in close proximity with each other, because that's how you can reduce the impedance of these conductors. And we'll get one in a second here. Voltage drop. This is the formula that we were talking about, guys. To voltage drop, E voltage drop equals 2 KIL over CM. The only thing I gave you guys instead of the 2, I said if your system is three-phase system, if it is a three-phase system, instead of the 2 becomes 1.73. Exactly the same formula that we use, except if this one that you're looking at is for if a three-phase system, instead of you put 1.73. Otherwise, if it's 2 KIL over CM, this is single-phase system. Single-phase system. Any guys about this formula for single-phase 2 KIL over CM? If it's three-phase, it's 1.73 instead of 2. Any questions? Any question? VD is the voltage drop. K is the ohm per mil, which is basically the resistivity of the system, and I is the current, length, and feet, and circular mil is the cross-section area. The voltage drop, phase, and single-phase calculation. I'll get an example guys in a second. Parallel conductors. When we parallel conductors, before we just cover the parallel conductors before we leave, guys. Suppose I have phase B and phase C here, and suppose I have also phase A and phase B and phase C here, and all these phases are tied together from one end through a log. As you can imagine, these conductors are log from both sides, right? That's what parallel conductors. You have them three conductors. And in the last phase here, let's suppose here's another phase A. These are the three phase C in this case. Is my log, and I'll draw this one in a second, and you can see how we parallel the conductors. So we just go back and tie these at the end here. Okay, we'll see that's what parallel conductors is all about, right? Tying at the end to the same log. That's what paralleling. Here's my phase A, here's my phase B, and here's my phase C conductors. And suppose I need a neutral, so I have to parallel my neutral phase, neutral 1, neutral 2, neutral 3. Time at the end, we'll log a 3 conductor log, and off you go with a parallel system. These guys are your conductors that parallel, tied at the end. This is my neutral. This is my neutral. So each of these conductors these are 3 conductors. Each one of them, my friends, are 500 kcm. I like 500 kcm. 500 kcm. And are the same thing, 500 kcm, 500 kcm. And let's just say the neutral was 400 kcm, smaller, 400 kcm. K, C, and M. And it was also 3 conductors. Why would we parallel conductors? The challenge is, guys, always comes. Why would you parallel? What paralleling conductor means? Conductors, I can't emphasize, guys. When you parallel conductor, you are tying them at the end. Can you get? You're tying the conductors at the end. That's basically what paralleling conductor is. If it for phase A, you're tying them at the end, and for phase B, and as well as for phase C, you go to the end and tie them at the end. Also for the neutral, the same thing. You go and you tie these conductors at the end. Why would we parallel, guys? We parallel because we can't carry the conductor into N. We can't carry the conductor, the current with the same conductor. The conductor is so big, so clumsy that I carry it. Here's the rule of thumb for a lot of people, guys, for paralleling. If your conductor is 500 kcm, if you can't carry them with 500 kcm, or the equivalent to it is 380 amps, more than 380 amps, or you need a conductor more than 500 kcm, you parallel. So suppose I have a 600 kcm, 600 channel. It's a good idea to parallel. Well, a couple of things that you guys have must be. What does paralleling mean? Tie them at the end. We parallel because we can't carry the conductor with one load with one conductor. A couple of rules. Number one, they have to be all the same length, same material, all copper or aluminum, the same size, kcm each, the same insulation, channel, and also terminated with the same lugs. And I add one more conduit, guys, the same type of conduit. Conduit, if you put them in a conduit to be the same conduit. And a third one, they have to be 1 aught or more. So, friend Joe, to parallel conductors, you cannot parallel less than 1 aught. Power, you can parallel for power less than 1 aught. Same length, same material, same circular mill, same insulation, same termination, same type of conduit, PVC, rigid, EMT, and the conductor cannot be less than 1 aught. Any question about the rules for paralleling conductors? Question about the rules for paralleling conductors? And about the rules for paralleling conductors, my friends? So basically, the rules for paralleling conductors in terms of rules. Okay, so that's I emphasize linked material, same length, same material, same circular mill, same insulation, same termination, same conduit type, and not less than 1 aught. Not less than 1 aught. That's the rules for parallel conductors. We parallel conductors, guys, due to magnet. What we do, you see here. Well, parallel conductor, guys, you're supposed to put all the conductors of the same circuit in the same conduit. So I have here's my phase A, here's phase B, and here's my phase C, neutral, and neutral. If you guys put the phase A, phase B, and a C and a neutral on the same conduit, what happens is you reduce the magnetic field of all these conductors kill each other. Short, you end up with lower impedance and less heat. Lower impedance, less heat. What you want to do, here's what you don't want to do. You don't want one conduit, especially steel. Steel is a rigid metal conduit. You don't bring one conductor, A conductor, and put it in one conduit, and phase B conductor in conduit, and phase C conductor in a third conduit, and the neutral in a fourth conduit. Do not by any means if it's a metallic conduit, especially steel. You, my friend Eric, you can do this with PVC. It's not a good idea, but you can do it with PVC. Suppose all the conductors of phase A in one conduit, all the conductors of phase B in one conduit, then in one conduit, the phase C in one conduit. If it's PVC non-metallic conduits, it's not a good idea though. But if you're putting them in a rigid steel, then you have to put all, as this is the most acceptable way, where all the conductors, phase A, phase B, and phase C in one conduit, and then second conduit will have the same thing, A, B, C, and neutral, A, B, C, and neutral, and so forth. Any question guys about paralleling? Any question about paralleling? Let's take a quick question about, here's let's just suppose that you guys have a 1000 amp switchboard, and I need to parallel the conductors that can switchboard, right? That's typical, parallel the conductors. All right. What I would do when I want to size the conductor for that baby, so 1000 amp. Remember, it's 1000 amp. What I would do, guys, is take the 1000, divide by 3, right? By 3, because 3 you want to be in the 300. So what? Take 1000 divided by 3 runs, that'll get you 33.3 amps. You guys, when you want to parallel, you want to stay with my rule. You stay in the 500 kcm, 500 k cnm, and 500 kcm guys can give you 380 on average. 3 amps. You stay within the 300, parallel, the best application in my book anyway. So if we divide by 3, that's 333. If you guys take this one to table 310, 3.16 under degree column because it's more than 100, and if you go there, I'll get you, what is it, 250 or 400? So 75, I have 333, 333, 333, 400. So you're going to 400. That'll get you 400. 400 K, C, and M. So what does that mean? How many conductors? Let's just say that's 4 conductors. So what does that mean, guys? What that means is I have my conduit number 1 here, my conduit number 1, conduit number 2, as you can imagine, and here's my number 3. That's the 3 runs, 3 sets, 3 sets. And inside each conduit, I'm going to take phase A, phase A, phase A, phase A inside each conduit, and then I'm going to go get my phase B, my phase B, my phase B, and my phase B, and you can imagine what comes after B. It's you're going to get your phase C. Here's my phase C, my phase C, and my phase C. And not to leave my neutral alone, I go grab my neutral in each one of them. Okay, my neutral. So this way, then you have 3 sets, what we call them 3 sets, right? Of 3 sets of 4 conductors, 4 conductors, 100 kcm each, 400 kcm each. That's what you're designing to carry 1000 amp switchgear. Any questions about paralleling? How do you size for paralleling? You take that 1000 amp divided by 3. Why 3? Why not 2? Can I divide it by 2? Yeah, no problem. If you divide it by 2, guys, will give you 500. Go to a 500. You also need 900 kcm. You need 2 sets of 900 kcm. I really damn, but working with 900 kcm is not fun at all. So if you, that's why 100 is a good cutoff to work with when you start paralleling it. You don't want higher than 500. If cable trays is a good idea to parallel that. But if you're pulling them in conduits, 500 is a good idea to parallel. Any question, guys, about paralleling conductors? Why parallel? Because you can't carry, it's too big of a conductor to carry. 2 conductors. What are the rules for paralleling from your friend Chad? Here's my rules. If I can't carry the load with 500 kcm, I parallel. Or if it is more than 380 amps, I parallel. Well, 400 amps, basically. If your load is more than, my panels are more than 400 amps, I parallel. No question asked. Any questions? Question? I can't emphasize, guys, without making a mess here. Parallel, now when you take see how we take these blues? These will be, I want to make a spaghetti here, but you guys can imagine these will be tied together from each conduit. Can you guys see that? And the last one, where's the last one? What color? And these will tie together. Can you guys see that? Together ends here. From both ends. And from here. Well, that's what paralleling is all about. That's what it is all about, tying them to carry them out of current at the end to the same lugs. It will really, we terminate them in the same lugs. There you go. And at the end here, and to be evenly, I want to go to my neutrals or terminate them in the same. Look at the beginning that you can get. So there you go. Okay, any question guys about parallel conductors? That's how we basically tie the switch gear. And if my switch gear is located let's use this one. My switch gear is located in this side. So here's all these will be inside my switch gear from this side and inside my transformer from the other side. Friends, any question about that? So friends, what parallel conductors is all about in terms of sizing for parallel conductors. One thing is when I have to show you a few things in the NEC code book. Oh, let me go. I must have moved fast. The question is, what are the rule of thumb for sizing the neutral? Here's how I size the neutral. Let's just go size the neutral for this system, guys, that we've just done. There you go. Size. Okay, I'm going to size the neutral for switch here, and that shouldn't take much work, guys. Let me just go grab this. So the neutral, I have my 1000 amp, and I'm going to do my neutral, right? You do, guys. I take the first 1000 amp. Remember, you can derate up to the first two. Remember that 200, leave them alone. I think, what is it? 60, I believe. First 200, leave them alone. Then take the 100, the 1000 minus 200, multiply this by 0.7. Okay. All right. What I'm going to do. So you end up with the following calculation, my friend. You end up basically with 200, 800, right? 800 times 7.7. This 7 is coming from 220.63, I believe. Okay, we take the 800 times 0.7 equals 200 equal. Oops. I have 760 amps. This is neutral load. Okay, so if I take this now, I'm going to take that's scenario probably 760 divided guys by 3 because I parallel 3. So if we divide by 3, 253 amps. 253.3 amps. Perfect, no problem. And then take my 253 amps and take table 3 times the 16 on the side. What is it? 253, 255. That's 250. 250. So get me one conductor. Remember, it's a neutral. Only conductor, 250 kCm. 250 C/M. As my neutral. So in a case like this, and remember, other phases were 400, right? The one that we just found was 400. We have a 400, and in a case like this, 400 is neutral. If I can find it, yeah, my neutral here will be 250. 250. Rule of thumb: if you want to run 1, 2, up to 3 steps below the neutral. I usually go 3 steps, no more than 3 steps below the phase. So my phase is what was it? Let's just say my phase was 500. I can go 400, 350, or up to 300. 100. So on this 400, we went 1, 2, or 1, 2, 3 steps to 250. There's a relation. So no more than 3 sizes below the phase. Does it make sense? On side neutral, usually you can derate anything higher. Not usually, by code, you create anything higher than 200 by 70%. Anybody has any question about that? If you fall neutral, that's okay, except you're pulling a lot of you're building a lot of copper, throwing a lot of copper in the ground. And the neutral is less than that. But you know, with panels, things change all the time. So that's the safest way of doing it. Go this way. Understanding of the code. Any questions, guys? Any questions, my friends? Good one. Okay, before we do you have switch gear, Joe, my friend. Before you switch, flip switch and off we go with energize, and we blow half of the building off. We need to do two things. We need to measure. Measures are, how many of you guys have used measures? Anybody have used measures? Ohm meters, power ohm meters to measure the, like, suppose you have a phase A, phase B, phase C here. Is my phase A, phase B, and C, and my neutral is my neutral. Guess what? All these are going to be in the conduit, of course, because we deal with conduits. Is my conduit here? How these three phases and neutral, and my conduit is mid conduit 3 and 3. If measure, here's my meter, here's my measure here, and I go. It has a battery, and you charge it, and off you go with the lead. Let's use this as a lead. So take one lead here. You're going to take it from phase A. One time, you're going to take it from phase A to the conduit. The insulation is intact, good. Then you should read very high resistance, extremely high. Then the insulation of phase A is perfect. Then you have the same lead, one, and go to phase and then lead move it to phase C, and same lead move it back to the neutral. So that will get you the insulation between the conduit, in this case between phase A, the way I'm showing it right now, between phase A and the conduit, phase A and phase B, phase A and phase C, and phase A and the neutral. So if you measure a very high impedance, this means insulation is in a good shape. Then you do the same thing for phase B. Then phase B, and you do it for all the phases. Phase B now needs to go to the conduit. I need to go like this, phase B and C. I need to go phase B to phase C, and also I need to go phase C and a neutral. So short, guys, you measure the impedance between every phase and the other phase, every phase and a neutral, and every phase and a conduit. If it's very extremely high, this means the insulation is perfect, no problem. If it's a short value, this means, guess what? When we will pulling phase A, we actually damage the insulation right here, and we are to energize. We will reverse phase to ground. Anything about the measure? Any question about using it before you energize the equipment? Any questions? Basically, what we do, before I give you guys the poll for night, I want to show you one other thing. Tables. So if we were to summarize, guys, we tried conductors based on 310/16. For load, we get based on voltage drop and the rating. You choose the largest conduit. I'm going to go ahead and share my desktop with you, and just go on the little thing here in a second. Okay, let's go. I want that you guys know how to use. Go grab that one, put it in here. And, okay. Put it right there. And okay, chat. Let's get chat here. So I'll grab the chat here. Take me a second and grab the insulation. Okay. So this one, guys, is table 3, chapter 8, chapter 9, table 8. And if I am to ask you, what is the circular mill of number 1 aught? No problem, Chad. Here's the circular mill, and I hope everybody knows how to find the circular mill. Later on, guys, when you go to your exam, they'll ask you about the resistance for an aluminum. Unless they tell you it's coded. So if I ask you, what's the resistance 1,000 feet for what? So if you come over here, this is ohm kilofoot, right, for 1,000 feet. And if you go all the way across, if one odd conductor, the resistance for every 1,000 feet of this cable would be 0.122. 0.122. Important things, guys, to identify. Had this conductor been aluminum, if this conductor will to aluminum, the same. Look at the resistance, how it almost doubles. Look at that, 0.201. So that's very important, guys, to know the stuff. These highlights, if you have not highlighted this, highlight stuff I'm highlighting right here in front of you. So you need to find the resistance. You need to be able to find the circular male. Now, people, guys, ask me, Chad, if I have 600 kcm, what's the circular male for 600 kcm? The circular for 600 kcm is not given, right? Because it's actually 600. 0, 0, 0. This is not the right color to write it. Let's go use it's the 600, right? K is 1,000. Can't believe people ask, which I can't find the cm for 600 kcm. Well, 600 kcm, buddy, 6,000 circular mil. The same thing for all these guys. The 50, and you can see they don't write them here because it's redundancy, right? 100, 400,000, 500,000, and so forth. All these. Any guys about how to use this table? Any question about how to use this table? Question about how to use this table? Thing that come all the time. Suppose you guys did a calculation. Suppose you did a calculation, and you did your calculation. You came up with let's just say you came up with 130.152. Suppose you came circular mill. You did a voltage drop calculation. You came up with this value. Then come under the circular mill and try to find the conductor that have 130,152 circular mill. Okay, let's see. Okay, here's let's start right here. 105. That's small. Let's start here. This is 133, and I need 130. Perfect. So the next standard then is basically my 133, right? 100. This is the standard after 130.152, right? 132.100 comes after 130.152 and translates in a language that we all understand into 2. So this conductor will actually be 2 ohms. Question: how to use that table to find the right conductor based on the circular mil. Again, how many people get confused with this? Any question? My friends? Another one that makes people confused. Suppose I have 321.536 circular mil. My calculation came up with 321,556 circular mil. So let's come over here. Oops, the second one is 2110, right? Then go to 250,000, 3. Oops, there you go, 3. Now it needs 321. The next after 300,000 is basically 350. So this will translate into 350 kcm. Any questions about how to use this table to find the conductor size? How to use this table to find the conductor size? I'm going to take you, if you guys don't have any question, I'm going to take you to NXB, and I don't know how many of you guys have been in this NXB. To give you an idea that ampacity is an interesting topic. So let's go, my friends, AB, NXB, I believe, NXB. All right, I'm going to go, this, and I'm going to go get rid of this here and go back into. I'm going to take you guys down to this is the AC all down to which should be table B. Okay, product safety, things in NXP that's really interesting. And if you have your code handy, I want you to go to table B3 10.7. Here's NXP. NXP guys give you more information about ampacity conductors for certain applications. I want you to pay attention, just a special attention to, let's go to one in particular, which is 310.7. I will highlight a few things in 310.5, 310.6, 310. Okay, 310.7, guys. I don't know how many of you guys have used this table. Anybody ever used this table? How about or no? Anybody ever used this table? This is the ampacity of, look at that, the ampacity of 3 single conductors rated the same thing up to 200 in underground ducts. Conductors per electrical duct, 3 conductors per electrical duct, based on ambient temperature of 20 Celsius or 68 Fahrenheit. Electrical duct per the configuration. Look at that configuration for it is based on these configurations, 310.2, which we're going to be looking at. Okay, nobody's there. Let's tell you. Let me just go. I want to get back to this, but I want to tell you the configuration, guys, that they're talking about. It should be not far from here, and we'll get back to it. So, suppose I have an underground bus duct, not bus duct, and I want to feed them. Here is my. Okay, here you go. This is a configuration that they use, guys. Paralleling. I want you guys to look at this. This configuration is the one that we're going to be using in a second here. So if I'm paralleling 6, these are 6 ducts parallel together. 1, 2, 3, 4, 5, 6. And configuration that's very common when you parallel conductor, guys. As a matter of fact, go as high as 9. So suppose I have a 500 kcm. I'm going to be using this one in particular, just to give you an idea. So I have 6 circuits in parallel in underground ducts encased in concrete, commonly used electrical ducts, 6 electrical. Each one of them has phase A, phase B, phase C in it. Okay, you can see that. So that version that we're going to be using. Also, you can put one duct at a time, 2 ducts. You kind of them. You can have a direct bury them right here, and all these configurations. I'm going to highlight this particular one. Just remember how it's going to look like when you see detail number 3. Okay. Now you guys have known where we are. Let's go back. This is how I put these 6 ducts back to my table number 7. Okay, table number 7. Okay, table number 8. Let's go all the way to table number 7. Okay, so you guys have seen how table number 8 is. The table I use duct 6 electrical ducts. Can you guys see that detail number 3? The one I just showed you. 6 electrical ducts. Since it's underground, I'm going to be using XHSW, and I have a 500 kcm conductor. With that 500 kcm conductor, if you put the 500 kcm conductor, 3 of them in a bus box like this, you can see them out of amps. Okay, with this you can carry 412, 273, and 340. So which one am I going to be choosing, Chad? Based on the resistivity of the earth, guys, wherever, and there's a software that can identify this one. If you don't know, usually you default to that one, and the load factor of 100%. That's your default, unless you know otherwise. At least my default. And based on that, then 500 kcm, beautiful 500 kcm, can carry only 273 amps. You guys remember how much current a kcm can carry? A kcm can carry 300, normally 380 amps. Can you get how low it can go under these circumstances, guys? From 380 amps all the way down to 273 amps. If I parallel 6 circuits in an underground encased concrete duct, you no longer can use the 380. You have to go all the way down to 273 amps. 273 amps. Think about this. I use engineers all the time, guys. I just wanted to emphasize this particular one because it's really interesting. Don't pay attention to when you put things in underground ducts in configuration. Ampacity you can't just use for 500 kcm 380. A lot of people, Eric, my friend, they go 380 and okay, 380 across. You have to use either these configurations or you have to use an amp calc software. And this is an end of any question, my friends, any question about this table. And of them are the same, guys, for different configuration, different installation, direct buried or less, or so either direct buried, you one conductor per conduit or 3 conductors per conduit, and so forth. Any question about this one, guys? I hope it didn't confuse you too much. That's the one I wanted to show. And last one, guys, in NEC code book. So please pay attention to NEC. NXB has a very interesting situation here. I'm going to go back to 310.15 here, and I'm going to go all the way to here, 310.60, and the same. You probably guys have seen the same configuration here for high voltage. These are in 310.60 for high voltage. The same configuration. These for high voltage installation. I'm sure some of you have seen these. The high voltage table 310.16. Look at that. So this is okay. Let's look at some of NEC and so forth, which is one that makes a little bit of sense. Base configuration. Okay. Okay, is the ampacity of no, I need to do one in the underground. Here you go. So for this one, ampacity of 3 single conductors cover in an underground duct, 3 conductors per duct based on an earth of this amount, the duct arrangement as I've seen it. And this is for the medium voltage. Okay, let me just see if I should go one more. This is configuration I showed you guys, except for medium voltage cable. Here, and this is detail. Remember detail 3, guys, 6 ducts. Voltage. Suppose I have a medium voltage 13.8. So this is going to be basically because I have 13.8. Suppose I'm using insulation 105. Then I'm going to use a 500 kcm conductor. I can carry 310 amps out of 500 kcm conductors. Yes, the amps are different. And again, this is for a 15 cable, 50 kV medium voltage dash 105 cable. I decided to use the most common one, which is 90 degree, the 90 degree column. You can out of that baby 290 amps, 190 amps. 380 that you can get out of 500 kcm PHR. About this medium voltage cable, these, if you're dealing with medium voltage, guys, these become very handy. Okay, this is only for 6 ducts carrying 6 conduits. 6 ducts carrying 6 circuits. Each one is 3 phase per duct. So interesting as you move through. And one I want to follow here, so all the medium voltage cable, if you're in the medium voltage cable, this is your baby. Here, so strongly suggest review. If you have any question, call me. I've used a few of them here over the years. So I'm going to go all the way. Here's the configuration, direct buried, all the way. I'm going to go to high temperature conductors, 3.20. Let's go to 16, 20, okay, here we go, 3.16. You guys are familiar with 3.16. This is the one that we were just using. Perfect check, right? But look at it, only for carrying conductors in a raceway, in a cable, or air directly buried. Directly buried conductors. Also apply to it far away from other conductors. Until you guys look at 310-17. 310-17 is stable for if you have conductors in a free air based on ambient temperature of 30 degrees. Free air. Conductors, single, this is allowable quantity of single insulated conductors in a free air based on ambient. So you have conduction and insulation. Let's look at the 500. The same thing. I like the 500 kcm, guys. Suppose I have my 500 kcm conductor in the air, and I have it. I have my insulation. Here's my 75. The same thing. 90. 75. So that if I put it on the air, look how much current I can get, guys, out of my my THHN conductor. Or in case I don't have THHN, I have, let's see, because it's in the air, it's THHW. Suppose because it has to be location, THHW outside. I carry 620 amps. Double the amount of the current, almost double the amount of amps I can carry out of 500 kcm if I put it on insulation outside on a pole. It's really interesting to see, guys, how you can see the huge difference. And the rating purposes, if I want to rate, it can go all the way to 700 kcm. So unreal. So these are something I wanted to mention just to get you an idea how the same conductor, the same insulation can get you different amps. This, how many have used high temperature conductors? High temperature conductors. Anybody have used high temperature conductors? High conductors. You're looking at it right in here. A conductor that's rated for 50, 200, or 250. So these are the high temperature conductors. Anybody have used high temperature conductors? The definition is Z, E, F, E, P, D, and P, F, A, and S, A. In places, guys, where the temperature, the ambient temperature is extremely hot. So look at this. It's allowable electricity for insulated conductors up to this voltage in an ambient temperature 150 all the way to 250. There should not more than 3 current conductors in a raceway, a cable, or in the air in an ambient temperature of 40. Look at the temperature is completely 40. So based on this one, guys, I can, let me just use, we don't have 500. They don't make it for 500. Let's look at 4 aught. 4 aught. Insulation is rated for 150. Look at how much 4 aught can carry. 332 amps. 4 aught, to give you an idea, guys. Normally 4 aught can carry only 230 amps. Normally 4 aught can carry 230 amps. We want the 320. And if it's an insulation 200, you can go all the way to 200. And if you use an insulation 250, you can go all the way to 361 amps. 361 amps. That this doesn't mean you can carry the same amount of amps. So, for example, we always buy lugs. Here's the lug. Here's the lug. This lug is for 75. You can't find lugs rated more than 75 for low voltage. 70. So, and I need a conductor to tie these two lugs together, guys. So here's my conductor, right? Landing on these two lugs. This conductor having to be a conductor. Let's say this conductor having to be a conductor T. I have T conductor, and TFE conductor is rated for 250. Okay, for 250. You guys look at the, and this conductor was 4 aught. 4 aught, right? TFE. Then this conductor can carry, it's supposed to be able to handle up to 361 amps, right? 51 amps. A minute. The logs, though the logs, if you can look at the logs themselves, guys, these logs, because they're rated, both logs here, they're not rated for 250. These logs are rated for actually 230 amps. There's 30 amps. And this also logs is rated for 230 amps. Okay, so how much current can this conductor carry? It's carried based on the weakest link, which is 230 amps. I can't more than 230 amps. The question becomes, my friend Joe, then why do I have these conductors? Who cares about them? These you get with the derating. So suppose that the temperature, suppose that my temperature was, okay, let's say my temperature, because these are very high temperature, suppose temperature was this amount. Can you see that? Remember, are going to be in a places where it's extremely hot, extremely hot. Look at the factor. Now I can use a 0.4 and by 361 amps, so it's 0.49 times 361 amps, and then, oops, what did they say? 0.49 times 301 amps. That will be 177. That will give me 177 amps. Okay, so from this conductor cannot carry more than 177. So what that means? This means it will give you a higher amp to start the rating from. Can you see that? Otherwise, I have to use a smaller amp. If it's not this insulation, then you have to go to 260 in effect. Had this been a THHN, had this been as a THHN, this would be, you have to go to 260. Look at that. You have to start with 260. So starting with 260 and ending up with a very small amount of amps, if you do 260 times the for 260 is use it for 4 hours, and for the same amount of temperature, what did we say? It doesn't even go, it doesn't even get high. It doesn't even the high 0.4. That's so 0.41 times 241 times 260. You have 5. If you use the THHN, you're going to end up with 107 amps. Look how small amount of amps that you can pull out of this conductor. So I'll give you an idea why we use these conductors. Look at the very high temperature, guys. They can go all the way up to extreme temperature. Unlike the THHN, these are rated for places in boilers and places where the ambient temperature can become really hot. Any question about that one? So I thought that that's worth make calculation about this table. I use this table. Let me ask anybody have ever used this table? Anybody before? The insulation FEP and PFAH, TFE. So, guys, you probably would finish your career without ever using this table. But it's idea to know that it exists if you have a situation where you have a high temperature application, like in boiler rooms. Place the temperature can be extremely hot in certain locations. There's a place that can melt steel and all these industries that create a huge inverter. Always pay attention to it, type Z, TFA, and TFE insulation. So that's basically what I thought about running these, and then you guys can get a scuba. I don't have time to get you the enter. Okay, let's close that one. And then you can see here. There's also 250 Z. Some of them are, look at the insulation type. There's copper, there's nickel, and nickel coated copper, and there's aluminum or copper clad aluminum. So these are the type of the conduits. Nickel here too. The same thing is, I don't know if you've seen that, guys. Same thing, copper is nickel or nickel coated copper or aluminum. So there are two different type of conductors. So these are things, places to look at. Okay, have for this one, let's go back. And there's a few of them, guys, that you can see the. All right, time to get you guys the poll. So please read the one in page. Here, page 225. All right, guys. Any question, my friends, before I let you go? With exercises, guys, that with that in page 2.5. If we have measures that it appears that, look at this one. It's 500 feet scroll of two conductors, number 12 bill wire. If you have 500 of them, and you can measure the impedance, and that one in labs, it's really interesting. All I have, I just want to remind you before I let you guys go, that not next week, the week after, we're going to have our class on the 18th. Now, guys, the 18th, instead of the, as I told you, right? The 18th. Everybody can you guys acknowledge that not next week, the week after, the class will be on the 18th instead of the 19th. Acknowledge that the 18th of April next week, the week after. Okay, 2 more classes, guys. Next week, we're going to talk about residential layout. So coming 2 weeks, guys, talking about laying out receptacles and branch circuits and feeders for residential buildings. And we will talk about residential load calculation and a few calculations, wires, and all this good stuff. So we're going to spend coming 2 days or meetings talking about calculation, and then the last meeting will be a review for the final. And that's the optional, as I said. Okay. Anything, guys? Any questions about what we heard? I hope I didn't make it too complicated for you. Nice. I remind you guys, you're going to have the exam, the block exam. This time, have your block exam. Block exam, I do not review the block exam. If you have any questions, please call me, email me. Well, the best thing to get me guys via email. If anything bothering you about one of these block exams, just feel free to drop me an email. Last reminder, if you guys have not done your homework, please do your homework, email to me. I collect them at this time. And that's at this time, collecting them. And any question, guys, before I let you go? Any questions? Any questions? Thank you, my friends. I hope that was informative, and we will see you next week on Tuesday. Next week will be Tuesday. Thank you. It can be done in segments. I believe so. Yeah, as long as you don't submit, Eric. If you can do it, as long as you don't submit the quiz. Absolutely.